Assalamualaikum and good morning. So we have a new topic for today, that is design of slabs. So today I will teach you how to design simply spotted. Before that, are you okay? Senyap je. Are you okay?
Okay, doktor.
Can see my slide, yeah? Okay. Okay. So we have, you have already know how to design beam, yeah? And now we're going to design the slab, yeah? So this diagram shows the slab. Yeah? This is for the simple building. So we have column, slab, and beam here, footing. Yeah. So in this course, you will cover the floor and the beam. Yeah? So we have already covered the beam. So now the slab. Miss everything, join. Okay. So this is the slab. Yeah? This is the picture after the slab cast. Okay, so this is the. Okay.
Doktor tak record ke?
Record.
Okay.
Record. Okay, this is the illustration of the slab surrounded by the beam. Yeah, this is the beam that you have already know how to design, and then this is the slab. Okay? So the slab, we have two type of slab, one way and also two-way slab. It's depend on the length of the side of the beam. Okay, so this is in construction. You can see this is the reinforcement for the beam. Yeah? You can see here. This is the beam. This is for the beam. This is for the column, and at the middle here is the slab. And you can see here more closer. This one. This is the beam. Okay, so this is the slab. So we know that the slab, we have reinforcement both way, in X direction and also LY direction, and the design will depend on the type of the slab. Okay, this is the your friend join in. Is Ahmad Zulkarnain. Okay, this flowchart shows how we are going to design with the slab. Yeah, basically the design similar to the beam, except here. Yeah, the slab that we are going to design, usually we will take the H less than 200 millimeter. Yeah, why? Because the checking for the deflection, if you choose greater than 200, then we need to calculate a long calculation. Yeah, last time you have learned how to checking for the slab, cracking for the slab. We have two types in Eurocode. The first type is that long calculation, and the second one is checking. Yeah, for the checking only, so we require that the slab less than 200. Okay, and then B, the B is always 1000. When you design the slab, bear in your mind that B is 1000 millimeter. And then we don't need to design the shear, yeah, because shear is usually less than the maximum shear in the concrete. So we just check, yeah? And then we check for deflection, cracking, and detailing. So the difference between the beam and the slab is that the thickness, and also the most important is B, 1000. Okay, this is the step. This is similar with the in the flowchart, but here I put this standard. The standard, yeah, you need to refer. For example, we need to design we need to determine design life. Yeah, is it 50 years, 100 years, and so on. Exposure class and also fire resistance. Yeah? So this one can be obtained in the table listed here. And then determine material strength, select size of thickness. Yeah. So the thickness we can assume or we can calculate by using the deflection, like the beam. Yeah? And then we calculate minimum cover for durability, fire, and bond requirement, and estimate action on the slab. In fact, we have already covered this one when we do the beam design. Yeah? Analyze structure to obtain critical moments and shear force. Also here we will use similar like the beam. Design flexural reinforcement. Yeah? Check for shear, deflection, cracking, and detailing. Okay. Atika join in. Okay, how to determine the slab thickness? Yeah, the slab thickness can be obtained by using the overall depth using the deflection control. Yeah? Deflection control criteria. And also, usually we consider that L over H, yeah, this is called deflection criteria, between 20 to 30. Yeah? It's just like, the method is just similar with the design of the beam. Last time the beam is 13 to 18, right? But for the slab, it is between 20 and 30. Okay. Here we have overall thickness. The thickness also can be determined. We have Matthew joining. Okay, thickness beside the L over H just now. We also can determine by looking at what is the standard fire resistance that we set for the design. For example, if your fire resistance is 60, the slab thickness, the minimum is 80 here. And this is the active distance. Yeah? Okay, so for the Ly over Lx, we have if it is less than 1.5, so the A 10. Yeah? This is to obtain the cover. Yeah? But we also can take this value, slab thickness, here as a guidance. Okay. Okay. The concrete cover is similar. Yeah, this is cover. Yeah, the cover. This is cover from the center to the outer surface of the concrete. This is cover. Cover, so that the D is between the center of the steel, H minus C minus diameter divided by 2, and the diameter of a steel is between 6 Okay, what is it?
Betul? Berapa?
Can you off the microphone?
Unsur S.
Okay, the diameter here is between 6 to 12 millimeter. Yeah, the diameter of the steel between 6 to 12 millimeter. Okay. someone want to join in? Alicia, Ame, and Ohan. Okay, so the D is between H minus C minus diameter over 2. Yeah. So this is the cover. Okay, we come to the analysis. Okay, the analysis. Okay, the analysis to determine the moment and also shear, we have like elastic analysis. What is elastic? Elastic such as moment distribution, moment deflection, yield line method. Have you heard about this yield line method in structure? Yeah, you learn this in structures. Hiller box strips. This is also in the structures, theory of structures. Moment and shear coefficient from code of practice or handbook. Yeah? So you can also use coefficient from the code of practice or handbook. Yeah? So it's up to you which method do you want to use. Okay, now how to design? Yeah? How to design the steel? Yeah? Once we get the moment and also shear force, the moment is to determine the steel. The steel that we here. This is the steel. The steel inside the slab. Okay, so remember during our design for the beam, yeah, but this time because this is slab, so the B is fixed to 1000. If B, we have the dimension of the B. Now when come to slab, B will be fixed 1000, and this is the steel, yeah, the steel. So we have a strain like this. So we assume that during ultimate limit state, the steel, the concrete at the outer layer here reach yield strain 0.0035, and at the steel level here is epsilon st. This is the strain of the steel, and we have the force here, yeah, force, and this is the force for the stress block. You can see here the strain and also the block. The block stress inside the slab is similar with the beam, except the B is 1000. So the D is equal H minus C diameter over 2. This can be obtained in Europe Code 1992 section 6.1. Okay, and this is the formula. Yeah, this can be obtained in the your design formula. We refer to the beam, yeah, the beam. So calculate K. Firstly, we calculate K. With the B here is equal 1000. And usually K will be less than 0.167. For the slab, basically we don't require compression reinforcement. Therefore, if you do the design and you find that K greater than K balance, there must be something wrong with your calculation. So you need to check whether your B 1000 or other value. Yeah. So now after that you get the Z. So Z must be less than 0.95D, and AS is equal M over 0.87 FYK Z. So this is the formula that we're going to use. Okay, this is related to the solid slab that we obtained in Eurocode. Yeah. Okay, your friend Matthew join in. Okay, here the code give information about minimum and maximum steel percentage. Yeah, and there is a secondary traverse reinforcement. Yeah, and the spacing. Yeah, it's the requirement for the flexural reinforcement just now is given in 931. Yeah. So let's look one by one. Okay. Okay, one-way slab. Yeah. When we design one-way slab, okay, remember what is one-way slab? It is the longest side divided by the shorter side here is greater than 2. So if there is 0.2, therefore it is one-way slab, and the slab will be spanning in this direction. Yeah, it must be spanning with a shorter direction. Yeah. So basically, if you forgot, let's say you forgot, you must remember, yeah, the failure of the slab will be happen here, parallel to the longer side here. Yeah. So it will crack like this. Yeah. Therefore, we need a steel to protect this crack, yeah, to avoid this crack. Therefore, the steel in this direction must be provided. Yeah, this is the steel, main steel here. Yeah, why it's main steel? Because it will protect the crack here. Okay. Therefore, from the side we can see that this beam, the red here, is the black one here that you can see here. This is main steel. Okay. This beam, this steel will be designed according to the just now you calculate K, Z, and AS. And the green one, since this is one-way slab, so we require secondary traverse steel here. This is traverse steel, and we must provide them with equal of 20% of main steel. Let's say here we got 100% main steel, AS. Let's say you 10 number of steel here. Therefore, you need to provide here must be greater than 20% of the main steel. Yeah. Okay. So this is the enlarge of this section. You can see here, the D is between the top to the center of the main steel. Okay. So the steel at LX direction. Yeah. So this is the LX direction. So when you analysis, Ahmad Zulkarnain, yeah. Okay, when you analysis, so when you analysis, we must consider 1 meter width. 1 meter width. Okay, 1 meter width. Here is 1 meter width. This is 1 meter width. The B is 1000 millimeter. Okay. Sorry. It's just now. So the B must be 1000 millimeter here. So meaning that if you have long slab, let's say 8 meter, then we design by taking into consideration B 1000, and then we repeat the design. Design only once, but will be applied for the 8 meter, something like that. Okay, this is one-way slab. When we determine that Ly over Li greater than 2, okay, I need to erase first. Okay, if you have Ly over Lx less or equal than 2, then we call it as two-way slab. Yeah, so we have this symbol. This symbol is called two-way slab. That means the steel will be into two directions. Will be provided into two directions because during ultimate limit state, remember last time, yeah, the pattern of cracking. The pattern of cracking. Something like that. So we have a crack like this. So in order to prevent this cracking, the red one is the crack pattern. So we need to provide, we need to provide steel in this direction, yeah, and also in this direction. So we have two types of steel. X direction. This is X direction. And this Y direction. Therefore, we need to put a lot of steel in this direction. We have a lot from here to here. We have a lot of steel, meaning that from here to here we have steel, a lot of steel like this. Yeah? We have a lot of steel. Something like that. Okay, until here, from here to here, spanning from here to here, and also this direction also the same. And during design, therefore we need only to show one of them only. Yeah, so one of them only you show only one steel here. Yeah? So we need to design both direction. Yeah? So for the LX direction, we have here the steel. The steel in X direction will be provided at the bottom. Yeah? Bottom face. Yeah? You can see here. This is the cover and this is the X direction at the bottom. And then the Y direction we put on top of the X direction here. Yeah. So when you see from this section, you will see that X direction in the dot here. So this is two-way slab, right? Okay. Okay, after we determine the reinforcement, then we need to check for the shear. Yeah? As I mentioned just now, the difference between the beam and also the slab is that for the beam we need to design the shearing, but for the slab we just check. Yeah? This is the VRD max. Remember VRD max? Shear resistant, yeah, in the concrete, yeah, in the slab, VRD. So we have CRD, K 100, rho 1, FCK to the power of 1/3, K1, sigma CP BWD. So what is the value for this? So here, yeah, and it's the minimum. So therefore, we need to calculate 6-A and then calculate 6-B. So in order to calculate 6-A, so K is given by this equation, rho 1 here. ASL is the area of steel. Yeah. Okay. So we can see, we will see at the example, this one. Okay, now the concrete cover. Okay, so it's not a concrete cover actually. This is the check for the deflection. Yeah. Okay, the deflection only will be checked at. Sorry. The deflection will be checking for the LX direction only. Yeah. Why? Because LX will give you a maximum moment. Yeah. So remember that. And then the cracking. Cracking is different from the beam because the value of the S max will be obtained from different formula. Okay. Let us see here. The minimum area of secondary reinforcement is 20% from AS min. Okay. Just now the traverse link is 20%. Yeah. That one is to avoid the cracking. Yeah. What is that? This is for the one-way slab. Yeah. Just now I explained that. One-way slab, this is one-way slab when Ly over Lx greater than 2. So it's only require main steel here, but we need to provide secondary traverse steel or secondary steel. This one, the blue dot, yeah, and the minimum is 20% of the main steel. Okay. Yeah. In area near to the support, is not necessary. Okay. The second one, the spacing of maximum, the spacing of principal reinforcement, that is the main steel. Principal reinforcement here is main steel, should not exceed 3 times overall depth of slab 3H or 400, whichever is the lesser. And the second reinforcement should also space between 3.5H or 450. Yeah? The rules apply for slab not exceeding 200 mm thick. Yeah, this is just what I say at the beginning of the lecture just now, earlier on, that if possible we put our H less than 200 because it allows us to do this simple checking for the cracking. That is by using the spacing of the bar not greater than 3H or 400 for the main steel, and secondary steel we limit the S max to 3.5H or 450. So here this is one-way slab, meaning that the blue reinforcement here, the spacing must less than S max 3H or 400, and this one, the secondary, must be less than 3.5H or 450 mm, which is lesser. Yeah. And for the two-way slab, both of them must be less than 3H or 400 mm. Yeah, so this is for the two-way slab. Okay. One-way slab types. So before we design, we need to identify the type of one-way slab. So just now I show you that one-way slab when Ly over Lx less than greater than 2. But sometimes in a construction, we will find that there's a slab only supported by 2 brick wall or 2 beam. You can see here, this is the brick wall or beam. Yeah? So here is the free edge. Yeah? This is also free edge. Therefore, if the slab is like this one, so we don't need to calculate what is Lx and Ly. Yeah? So we need to imagine what is the pattern of cracking. Of course, yeah, the cracking will be happen at this, at the center of the slab. Because here we have the support, of course it will crack or break at the middle here. Therefore, what we need to design is that we must design the steel, yeah, to overcome this crack, this one. Therefore, our beam, our slab, yeah, this is the thickness of the slab. So we need to put our steel here, following this direction, yeah. We call it here LEF, effective from center of the beam to center of the beam. Here we call it L effective. So we need to design it using this pen. Therefore, by taking 1 meter width from here to here, 1 meter width. So this is the slab. 1 meter width. We calculate the loading, the GK, the QK, and then we find the moment. So the formula is just like this. This is the simply supported slab. Okay. So the moment we get here, we can get the steel here, the black steel, main steel, and the red one is the secondary steel. You don't need to design, but the amount is 20% of the area of the steel in the black color. So that is the design of the slab for this kind of slab. So before design slab, you need to imagine where's the cracking, pattern of cracking, and is it one-way slab or two-way slab? Okay, now this is another pattern of one-way slab. Okay, similar like just now, previous one. Here we have the brick or beam, yeah, brick wall or beam provided of being a support, yeah, at the longer side. Yeah. Therefore, this edge is free. Here is free. We can see this type, yeah, in bridge at our kampong. Yeah? Basically, the kampong people, kampong people, they will build the bridge, yeah? Like this. Yeah? So in this case, if you want to design, just imagine where the cracking will be occurred. Yeah, during ultimate limit state, it will occur in this direction. Yeah? Therefore, you need to design this L as your span, direction of the slab. Yeah. So you will require the steel in this direction, yeah, to overcome this crack. So we need the steel here. From here to here, we have a lot of steel. So we had a lot of steel from here to here. A lot of steel. Just show only once here. Therefore, the black one here represent this one here. And the red one here is the secondary steel. Okay. Okay, this diagram shows you the one-way slab with the beam. Yeah, we can see here this is the slab and this is the beam. This is one-way slab, yeah, because we don't have beam here at the end here. So this is the beam. This is the beam. Yeah? So this is one-way slab. Okay. Now we have one-way slab type. Let's say we have a one-way Ly over Lx. Yeah? This is the slab that's surrounded by the beam. Yeah. So you can see here the beam. So you need to calculate Ly over Lx. If it is Ly over Lx greater than 2, so we need to design only in this X direction. You don't need design in Y direction. Why? Because during the ultimate limit state, the beam will crack in this way. Yeah? So we need to design the steel in this direction to avoid the crack. So we need this steel. So this steel in this LX direction. Therefore, we design this direction only. And this is become the main steel. Here, the black, the steel in black, and the red is the secondary steel with the moment maximum WX/8. Okay. Okay, again, this is the slab, yeah. 2 panels, 2 slab panel. Yeah, again, we need to check the Ly over Lx. If Ly over Lx greater than 2, therefore, you need to imagine the pattern of crack. Yeah? So for the first panel, the crack must be in this direction, and the second slab also in this direction. Therefore, we need a steel to avoid this crack, that is in this direction and also in this direction. Okay, therefore we know that this panel also one way, this one also one way. Therefore, during the design, what we can do is that just take 1 meter width of the slab, yeah, here, represent for all these 2 panels, just only 1 meter, and this is the configuration with the Lx. Yeah, calculate the moment maximum for the 1 meter here, then you obtain the steel, main steel, and also the secondary steel. Okay. Okay, how about this? Yeah. Okay, if you have a series of slab like this, yeah, yeah, this is free. You can see here there's no beam here, and this is not there's no beam. Yeah, what you can do is that imagine where's the cracking. Yeah, the crack will be happen here at the middle. Yeah, happen at the middle here. Happen also at the middle here. Therefore, we need a reinforcement to avoid the crack. Yeah? So the reinforcement required is that in this direction, this one, this direction, here also this direction, and this is also the direction. Therefore, we need to design it as, you know, from here to here, straight from here to here, yeah, because this is continuous slab. Yeah, this is continuous slab. P1 panel here continuous with the panel, and this panel continuous with this panel. This panel continuous with this panel. Therefore, we cannot design it as simply spotted, yeah, because this is continuous slab. Therefore, we need to obtain 1 meter width, and we design it as continuous one-way slab like this. Yeah? So we need to find what is the moment delivered by this 1 meter width continuous beam. So the moment, basically we have a diagram like this. Okay. Any question? Ada soalan?
Tak ada, doktor.
Yeah, okay. Tak apa, kita pergi tengok contoh. Okay. So now we have a very simple slab, yeah, with the B and L. Okay, so this is the brick wall, the brick wall. The effective span has been given here, 4.25. That means between the center of the brick wall to the center the next brick wall is 4.25. So B, we do B. Yeah, we don't need the value of B, because the design of the slab is actually 1 meter width. So the parameter that we want is that L effective. So here is given 4.25. Okay, the action GK on the slab, GK is 1.0. Yeah, 1.0 is due to the finishes like the tiles, the cement screen, and so on. Yeah. Jauzi, join in. Okay, so this is excluding self-weight. QK, the QK. What is the QK here? It depends on the function. Yeah. For example, here is the part of the school building. Yeah? So it's 3 kilonewton per meter square. Design life given is 50 years. Normal building. Fire resistant R60. And exposure classes XC3. Okay, the characteristic FCK 30 given here, obtained from table F. Yeah. Characteristic strength steel 500, unit weight concrete 25. You need to remember. Assume the bar is 12. So you can assume 8, 10, 12, or even 6. Yeah? The smaller diameter, right? Therefore, what we need to find is that the thickness of the slab. Yeah? Here is not given the thickness. Therefore, we need to find what is the thickness of the slab. Yeah? It's just like your project. You need to find what is H. Yeah? The H. You can assume, yeah, but we can also calculate the slab thickness. Yeah. Okay. Now, minimum thickness for fire resistant. Yeah. Remember just now the fire resistant. Look at the formula and design rule. Fire resistant. Fire resistant for the slab. Here table 5.8. One way or two way slab. So 60. So we have thickness 80, right? The H. If we constant with the fire resistant R60, so we got 680 here. Okay, we got 80. Therefore here we got 80. Estimated thickness considering deflection control. Just now we got L over H between 20 to 30. Yeah, let's say you take 26. You can also like 20, because there is 20 to 30. So any value between the range. So now let's say we have 26. So we have 163. Yeah. So 163 the minimum value due to deflection control. Yeah, this is for the fire resistant. So we need to take this one, yeah, as our thickness. So we have 175. Yeah, 1663. You round it up to 25 millimeter, the nearest 25 millimeter. So you got 175 millimeter, and then calculate the cover. Yeah, because the cover is not given. This is similar when we do the beam. Yeah, the first one is looking at the bond. Yeah, because of the steel that we going use is the 12 diameter. Therefore, due to bond is 12 millimeter. And then minimum cover due to durability. Yeah, what is the durability? You got XC3. Yeah, XC3 just now. Okay, XC3 durability. Yeah. Where's is the table for the durability. Okay. We have XC3. This is the slab. Yeah, design working life. Okay. Remember last time to determine S, yeah, before you obtain the cover, we need to calculate what is it? S that we require, yeah? The structural class. We must consider that the default is S4. Yeah? So you need to calculate what is S. So your S here is equal. We need to calculate what S we require. Yeah? So it's depend on the design working life. Yeah? Our design working life is 50, so therefore we omit here. Yeah, we got 4 just now. Yeah. Here 0. Strength classes 30. Our is 30, so less than, so you don't reduce it because our concrete is 30 just now. So if you let's say you put 35, then you need to reduce -1. So we don't minus here. Member with slab geometry, so reduce by 1. Reduce by 1. Special quality control. Let's say we don't bother about quality control, so we have S3. Therefore, from here, go back to this table. Minimum cover for the steel here, S3 here. Therefore, by referring to the S3, here S3, and then XC3. So the value of the cover is 20 millimeter. Okay, so let's see what is the value. Okay, here is 20 millimeter. Yeah? So you got 20 millimeter here. Okay, minimum exist dimension for R60. So where did we get here? Okay, now look at the formula here just now for the okay 60. The one way spanning slab is 20 here. The value is 20 here. A minute, please. Sorry, there is an interruption. My cat wants to go out. Okay, R60, so we have 20. That's why now we have 20 here. A, 20. And then the formula, using the formula, C mean is A minus the above over 2. So you got 14. Therefore, the deviation is 10. Yeah? This is fixed. Therefore, from these two value, get a maximum 1. So is 20. So 20 plus 10 here. So we got C norm is 30. So we have the value now is 30. We don't need to modify because it's already value. Okay. After that, this is the action analysis. Yeah. Now, before that, we must consider, we must imagine before we design. This is one-way slab, because it's only supported by 2 bricks, and the failure will be happen at the middle here. Therefore, our design, the span design is L, L here. Therefore, we need to take 1 meter width, 1 meter width from this slab, 1 meter width, 1 meter width here. Take 1 meter width here with the length L, okay? Therefore, So this is our slab configuration. This is very important. Before we start design, you need to imagine where's the crack will happen, and then what is the span that we need to take into account. If you got the wrong L, then your design will be wrong. So therefore, you need to imagine the cracking pattern and then determine the span of the slab that you're gonna design. Okay, now the action. The action just now we got the slab height. Therefore, you can find the slab self-weight. This is the height of the slab times the density, not the concrete strength. This is the concrete density. So we got 4.38. Permanent load excluding self-weight just now given 1.0. Therefore, you need to calculate up here 5.38. And then this is the variable action given 3.00 kilonewton per meter square. And then the design action. This is on the slab. Let's say we name it as ND 1.35 GK plus 1.5 QK. So we got 11.76. Remember, this is per meter square. Our design is per meter. Then you need to multiply by 1. So we get the new value here, 11.76 kilonewton per meter. Although the value is still the same, but the unit here, kilonewton per meter. Okay, because we multiplied by 1 meter width. Okay, now we have our design load on the slab 11.76 with the L effective 4.25. Therefore, we need to find what is, as usual, we will find the shear force and also bending moment. Since this is simply spotted slab, so we use this formula. So we get moment 26.5. The next, our next design is to design main reinforcement. So we need to calculate the D. Remember just now the D? The D is from the top to the center. Here. D is H minus C minus diameter over 2. Okay. So remember this equation? C norm, bar 2. Okay, 139. And then K is equal MBD square FCK. So remember, bear in your mind here, don't forget 1,000. 1,000. Because we are designing the slab, not the beam. So your K must be compared with the 0.167 because we don't do the redistribution. Okay, so K is less than 0.046. Therefore, we don't require compression reinforcement. Calculate the Z. So if your Z greater than 0.95D, just take value of 0.95D, then calculate AS, replace Z 0. With the value Z obtained by using 0.95D. So you got 462 millimeters square per meter. Look at the value here. Millimeter square per meter because we designed 1 meter width. So how do we get the main bar? Okay, look at the table. Before we look at the table, we must check first. Is it our value here is valid? The area reinforcement here must be in between the maximum and minimum. So minimum, but the minimum value, the formula is just similar with the formula used in the beam. So you got 0.26 FCTM mean tensile in concrete BD. So you got 209 the minimum at least. And maximum is 7,000. Therefore, what you got here 462 is in between. Therefore, our steel that we will provide will be based on this value. So let's go to see what is the number of steel that we require, that we provide. Look at the, where is it? Okay, now. So we have two tables. Look at the table B. Sectional area per meter width for various bar spacing. Look at here, millimeter square over meter. Okay, now we have 12 diameter. Okay, our one is 4/6 something, yeah, 4/6 something. So the appropriate value is 503. Therefore, H12, the spacing is 225. H12, 225, slightly greater than 462. For the secondary bar, remember for the secondary bar, at least 20% from 562. So if 20%, what is 20% for 562? 462 times 0.2, 92. Yeah, it's if it is 20%, 0.2 times 462. So you got 92. Yeah, only 92 millimeter per meter square. Yeah, so. Okay, it's very small. Then you can also refer AS min. Basically, designer will refer to the AS min rather than the 20% as required by the code. Just now in the code here, in the code. Yeah, here 20%, right? 20%. But designer like to use AS min. Therefore, 209. Look at the table here. 209. Use the same diameter. 209. Yeah, it's not in the table. Yeah, it's not in the table, but you can calculate. But you can also use H12 300. Yeah. Or from the calculation 450. Yeah. Here if is 300. So you got 377. It's greater than this one. Yeah. Okay. After we finish design the what do you call flexural reinforcement, the next step is checking for the shear. Yeah, this is the formula given in the code just now. The formula is 0.12 K 100 rho 1 FCK. Yeah. So the K value obtained here, input the D, so you got 2.20. Yeah. So it is greater than 2, so you use 2. Yeah, because K must less or equal than 2. So what you found here is greater than 2, therefore we use 2. Rho 1 is ASL, just now 503 divided by D, so you got 0.0036. So input the value in this equation, so you got this value and V min. Yeah, therefore this is in concrete that we designed is 73.9. The minimum is 75.4. Yeah, therefore VRDC is equal 75.4. Between these two is greater than the VED. Yeah, this is from the load, shear from the load 25, but minimum in the concrete is 75. Then it is okay. Yeah, we don't need any modification of thickness. Okay, the deflection, again the deflection is similar with the beam. Yeah, except the B is 1000 here, using the same formula, the same method. So we calculate the LD actual compared with the allowable. So our allowable 36.6, actual 30.6. Okay, cracking. Yeah, this is different from the slab. When we talk about cracking, just now the cracking will be avoided if we put the AS mean, the secondary. Yeah, secondary. We already put the secondary just now. And another one is the checking for the S max. Yeah. No, now our H is 175 less than 200. Therefore, we can use the guidance S max 3H here and 3.5H here as the method to control the cracking. If your H is 200, more than 200 or 200, then you need to use another method. Just for the main bar, just now we have 3H225. Yeah? So our S max maximum allowable here is 3H. Yeah? Calculate the 3H. 3 times 175. Yeah, it must be less than 400. I guess it's greater than 400. Therefore, our S max here is 400. So our bus spacing is 225 just now. 225 because 3 H12 225. So it is less than the maximum here. For the secondary bar, 450. Then just now we changed 300. It's less than maximum here. Therefore, our detailing, this is the detailing. Okay, the detailing for the slab. Okay, the detailing for the slab consists of two, the plan and also the cross section. Okay, it is easy if we use the cross section first. For me, I will draw in the cross section. I just draw the plan first without the reinforcement and then draw the cross section. If you can see here, the black one is the main steel. The main steel. The main steel will be provided from here to here. According to this arrow. There will be a lot of steel in this direction. So we need to show only one. And in the cross section, you show it in the cross section, in the bold color here. Okay, and number it as 0.1, while the distribution or secondary reinforcement, I will put it on top of the main steel. Or we need to show it also in the plan here, from here to here. A lot of steel here, but we need to show it only one. Okay, this is the how we arrange the steel. Okay, in the design and formula booklet, we also have the simplified rule. Okay, this is for the slab. Okay. The first one is the simply spotted slab. This is 100%. Remember, just now we have H and H12 to 5. So it can be, we can, extend it all to the support, or you can cut it, leave it 50% at least to the beyond the center of the support, with the spacing here, LBD, the extension here. The extension, you can see here, this is the LBD. Is it? This is LBD, the LBD here, LBD. So 15% of them can be extended to the support, beyond the support with the anchorage length. This is called anchorage length. Here is to provide bonding, bonding between the concrete and the slab here. Okay, so what is LBD? LBD is the value for the last time LBD. What is LBD? Design anchorage length. So LBD, you can find LBD in the detailing rule. LBD. Okay, LBD. This is L effective. How to calculate L effective? Usually LBD is 12 diameter, 12 diameter. Maybe there is in the book, there is guidance in the book. I'm not sure, is it in here? LBD is the length of the anchorage length. Okay, what is the anchorage length? Let's find anchorage length. Find anchorage length. Anchorage length. ANCHORAGE length. Anchorage length. Next, anchorage length. Oh, it's not in here. Okay, never mind. It is equal with 12 diameter, yeah. This one, the bending here, LBD is 12 diameter. The simplified rule, LBD is 12 diameter. See? LBD is equal 12 diameter times the diameter. Okay. Therefore, in your design here, the steel here, you can see here the hoop here, yeah, is 12 diameter. The hoop, sorry, erase. The hoop here, you can see the hoop here. This is 12 diameter. 12 times the diameter. 12 times 12, 44 millimeter must be bent up here to provide the bond between concrete and the steel. Okay? Any question? Any question?
Ada, Doktor.
Pandai ya?